Welcome back. So we're right now trying to evaluate the energy cost of adaptation, and I'm arguing that it's another version of defiance. And I wanted to take a bit of a detour in order to produce, by specific example, a theorem on entropy production. So maybe I should write those words down. A theorem on entropy production. And you'll recall that we already did this in the context of the, uh, the motion of molecules down their concentration gradient. So, you know, the specific example we did previously, we had dissipation of a concentration gradient. And so in that case, dg by dt was really equal to minus t ds by dt. The reason being that we didn't include any internal energy in our description. I can repair that later, and so that implies that ds by dt entropy production was equal to minus 1 over capital T of dg by dt, and that will yield kb log of c1 c2 and then times j delta y delta z. So that's what we did last time. We had worked out the entropy production for the motion of the molecules down their gradient, and the observation I want to make is that this was the net flux. That was the total, the net. And what I want to do now is I want to take a detour and I want to write it as the separate contributions due to the left to right flux and the right to left flux. And the reason for that is that there's a theorem that is very popular, which says that the entropy production rate, so I'm going to want to invoke this, the entropy production rate is given by a sum over, all the states A and B of JAB minus JBA, and then there's KB in front, and a log of JAB over JBA. Note that this thing is going to be greater than 0. The reason I say that is let's look at the case where JAB is greater than JBA. Then the thing in parentheses is going to be greater than 0, as is the log. And vice versa. If JBA is greater than JAB, then JAB minus JBA, the thing in parentheses will be negative. But then I will have log of a fraction, and that will be negative as well, and so I still get a net positive. So this is a general statement, and I will want to use it. And I'm going to give you a heuristic argument by example. And what we're going to do is we're going to use the dissipation of our concentration gradient again. I hope I can figure this out. So let's go back to our diagram. We had a partition, and then we had some molecules on each side, and what I want to say now is that I'm gonna call this left for L, and then this slide I'm going to call right, so that's going to be R. And what I want to say is that J left to right is equal to K hop. So this really takes us back to our earlier thinking about diffusion. So you'll recall that, when we did the chemical master equation treatment of diffusion, we imagined that each molecule had a probability k hop delta t of jumping during a given time step. So there's a k hop, and then times the number on the left, and that basically tells me the flux of molecules going from left to right, and I can rewrite this as k hop, and then times concentration left times delta x, delta y, delta z. And similarly, I have that j right left is going to be k hop and right, and I can rewrite that also as k hop times c right, and then delta x, delta y, delta z, delta z. All right, so that's good. And now recall that that we said that the delta G for one molecule was equal to, as you saw in this diagram, it's equal to this quantity. If I'm going from C1 to C2, so delta G one molecule is minus kBt, and then log of C start and C finish. What do I mean by that? So that's the side you go from to the side you start from, and the side you finish on if you're the molecule. In other words, I take the molecule from the side that has concentration C start, and I put it over on the side where the concentration is C finish. And so if C start is greater than C finish, then the free energy change will be negative because I have log of a positive of something greater than 1. And if C start is less than C finish, then I'm taking something up its gradient, and I'm going to have a net delta G that is what I want to say, that is positive. Okay, so what I'm going to claim now is that dg t by dt total is equal to dg by dt of the left goes to right stuff plus dg by dt of the right to left stuff. So what I'm going to do is I'm breaking up what I did earlier as the net. Here's the net. I'm going to now break it up into its two constituent pieces, the left-right transport and then the right-left. So let's think about that. So this is going to be given by minus kBt and then log of C left over C right, and then times J left right, delta Y, delta Z. And then this next one is going to be minus kBt and then log of C right over C left times, let's see, didn't leave myself enough room, times J right left, and then delta Y, delta Z. So let's recast this thing. I can always rewrite that as kBt log C left over C right. So now I've gotten rid of that minus sign. And so the net result is that I'm left with kBt, and then I'm left with J right left minus J left right, and then the log of C left over C right. This is and then times the delta Y, delta Z. Sorry, I forgot that part. Okay, this is looking interesting and promising, and now I go back up earlier, and I notice that I can write. So let me bring these things down here. So I had these two facts. So I can use these to rewrite C left as J left right over K hop delta X, delta Y, delta Z. And similarly, C right is equal to J right left, K hop delta X, delta Y, delta Z. Let's plug those in up here, and what we're left with is dg by dt, tot, is equal to kbt j right left minus j left right times log of j left right over j right left, which finally I can write as minus kbt j left right minus j right left times log of j left right over j right left. Great. I was sloppy about my delta y delta z. Sorry about that. I need to keep that. And finally, this tells me that ds by dt is minus 1 over t dg by dt. And so my entropy production is kb j left right minus j right left log of j left right over j right left. And this is my big result that I wanted to obtain as a precursor to the things we're about to tackle. So this is a special case of the much more general entropy production theorem or definition. I don't know what to call it, law or something. I have to think about that. If I like being semantically precise, but I'm not on top of that. This is equivalent, by the way, to this thing that I wrote earlier. So basically what I've done is, in one particular case, I've shown you that the entropy production can be written as the difference in the fluxes of the two pieces making up the net, and then the log of the ratios of those fluxes. And I will be using this for a variety of other things in order to assess this whole matter of defiance.